Welcome to episode number 24 of the ISTC Tailboard Talks podcast. I'm your host, Mark. Jerry is out on assignment, finally doing some work, so he won't be with us today. This is, again, episode 24 and the second in a series episodes that we're doing around equipotential zones and field safety with our special guest, Jim Vaughn. The first one that hopefully you have caught by now was episode 23, which was EPZ, the law and the principles. So if you haven't had an opportunity to listen to that podcast, this series is really a building block, right? So the first one was the foundation. Today's will build on that foundation and so on as we go through this series. So really, for everything to make sense, I would highly suggest you listen to episode 23 before you jump into episode 24. The other thing, if you're listening to this podcast series and you have questions about anything that Jim or I talk about or mention, you can send questions to Mark at ispconline.com, and I will gather those questions. And if we need to, we will do a final episode in this series around Q&A to make sure that we get everybody's questions answered and make sure everybody's on the same page when it comes to EPZ in the work zone. Again, today's episode is EPZ for Distribution and URD. The podcast of our sponsor today is T&D PowerSkills. So today's safety and training managers need flexible, effective solutions, and that's where T&D PowerSkills comes in. With a 78-unit curriculum designed for adult learners, you can control your training structure, control the scale of your delivery, and control your costs. Whether you're training a few crews or running a full apprenticeship program, visit tdpowerskills.com to learn more. Again, that's tdpowerskills.com. Again, special guest today, Jim Vaughn, Senior Consultant for the Institute for Safety in Power Line Construction, industry expert in grounding and bonding and safety and many other things. So welcome, Jim. How you doing again?
Doing lovely. Thank you, Mark, for the opportunity to participate here. This is important. I'm glad we get a chance to do it.
Yeah, I know we've talked about many times, and I think we talked about it on the last episode. We still continue to get out there when we're doing consulting work for companies. It sometimes amazes me, and it probably shouldn't, but I kind of always maybe take a half step back on the amount of questions and pushback and so on that we get around equipotential grounding, right? And why do I need to do that? And we don't need to do that, and all those. So I just felt it was really important, to do this episode or this podcast series of episodes to hopefully at least get people pointed in the right direction. And, hopefully we can do that and get people, or at least give them the tools they need to maybe make some better decisions when it comes to equipotential grounding. Because at the end of the day, and nobody can attest better than you with all the litigation work you do, we're still injuring a lot of people when it comes to our personal protective grounding. And unfortunately, probably the biggest part of that is the way people are installing their personal protective grounds. They think they're doing the right thing. They think they're protecting themselves. And at the end of the day, they find out that the way they installed their personal protective grounding is the reason they're getting hurt. Hopefully we can help with some of that here. Yeah, go ahead. You want to?
I was just going to say, and to reinforce what you were saying, and I hope that the podcast listeners understand that we at ISPC, we have a unique perspective because we do these litigation supports. Mm-hmm. Because when we do litigation, we have become, just by word of mouth, experts on grounding, mm-hmm. on personal protective grounding and on equipotential grounding. And when one lawyer in some part of the country has a case that we've done and we've been successful in helping them build a strategy and successful in the litigation, then they go on a record, and then another lawyer asks, "Well, who was it?" And so we get constantly get these inquiries on these litigations, and you'd be surprised how many of them are taking place.
Mm-hmm.
I've done now more than 24 litigations involving personal protective grounding where the worker was killed by the grounding that they installed to protect themselves because they did not properly install the grounding. They were exposed to a potential either because of induction current or normal flowing current or because of fault current. And when that occurred, they received a lethal electrical shock because the grounding didn't protect them.
Mm-hmm.
And if I encourage you to go back, like Mark said, to listen to the earlier presentation because we get into more about the principles of how equipotential grounding works, and that's the part that people don't understand. So when we are discussing this today, we are talking about principles that we have seen in place in action or inaction that
Yeah.
these things really do work, and that's the reason why it has such a personal interest for us to get this message out there
Yeah.
for you in the field.
Yeah. Couldn't agree more. Okay. In our ISPC Tailboard Talk topic, again, with this podcast series of episodes, I'm really just going to touch on the same exact thing at the beginning of each episode. And when it comes to OSHA 1910-269 N3, as you had heard the explanation in episode 1 of this series, right? Temporary protective grounds shall be placed at such locations and arranged in such a manner that the employer can demonstrate will prevent each employee from being exposed to hazardous differences in electrical potential. And like Jim explained in the first episode, this rule has really been around since the mid 90s. And with the 2014 update, specifically called this rule out as an equipotential zone because of the misunderstanding that OSHA made the assumption that when they stated this rule, that they just assumed everybody understood it was an equipotential zone, right? And I guess, for this one, Jim, I don't think we necessarily need to beat that to death, but I guess maybe the question would be when it comes to grounding and bonding, right, and creating those equipotential zones, what does OSHA say, if anything, other than this one rule, when it comes to grounding and bonding in the overhead and underground distribution world, right? Like, is there clear direction there? What does OSHA tell folks or tell us in the industry that we need to do when it comes to overhead and underground distribution?
Well, the rule is this is the only rule. The one that you read is the only one that actually uses the phrase equipotential zone.
Okay.
But it actually applies to every situation in its language because it says temporary protected grounds shall be placed in such locations arranged in such a manner. And that applies to everything, whether you are grounding trucks or whether you're grounding in a substation or transmission, whether you're grounding for the possibility of fault current, or whether you're grounding for induction, or whether you're grounding distribution, or whether you're grounding in URD. The rule is the same and the language is the same and it applies to everything. The problem is that the assumption is that everybody knows how to apply the rule according to the conditions. And
Mm-hmm.
that's just not the case.
Right.
When we do audits of employers and we go out and we talk to the people on the crews and we read the rules and we read their procedures, we can tell that they have a lack of understanding of what the requirements are. So sometimes we have we'll see rules that have one application that is supposed to apply to everybody. And then we go to another employer, they've got a 300-page grounding manual that tries to show the connections for absolutely every situation that's going to be out there. But then the people that are using that are not appropriately trained, so they don't, they just say, oh, connect this to that, connect this to that. And that's not good enough. We need to understand these principles and understand what this bonding is that we're talking about.
Yeah.
So when it comes to the rule, like I said, that's the only rule that's out there,
Okay.
for equipotential grounding.
Yeah.
But what you will find is if you do the research, that in the research tells you to refer to what's known as Subpart R, Appendix C. Appendix C is an application guide for installing worker protection using grounded equipotential systems. Tells you pretty much how to do it. And in the beginning of Appendix C, it says that if the employer complies with this section, they will be considered in compliance with the requirements for the standard. And they go through and they do make some suggestions, and we'll probably be talking about a couple of those suggestions that they make. That doesn't mean it's the absolute. It's not the only way that you can do it. It's one way that you can do it. And if you do it, OSHA likes that idea. But there are other ways to accomplish the exact same goal.
Yeah. 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 And I think a really good point you made was there's no black and white here, right? There's no, this works every time on this system, this works every time on this system, this works every time on this system. The workers need to be trained and understand and be able to identify, right, the path or the pathways that their grounding is that that they're installing, the potential current paths and so on that they're developing by installing their grounds. And we'll get into that a little bit more as we go here, but OSHA doesn't tell us how we need to do this. They just tell us how we need to comply, and then it's up to us, the workers in the field, and so on, and the employers on how we're going to make that happen.
And I will tell you that when we go and we will advise on behalf of employers, and sometimes we actually do a third party investigation, but we often go to help an employer maneuver and navigate around OSHA. OSHA is going to come in and they're going to do an investigation. OSHA doesn't know a whole lot more about grounding than what's the proverbial man in the moon. They have a book too, and they go and they look at the book, and then they'll say, well, the first question that usually is, well, what kind of training did you do? And that's the very first question they also ask of the people in the field. They said, what kind of training have you had? And then they'll say, what do you think happened? And if there's 10 people in the work area and you had an incident involving, a shock or an electrocution, well, not a shock, they don't investigate shocks, they investigate electrocutions that result in a fatality. And I had a case where there were 10 people on the ground and in the air, and OSHA interviewed each one of them, and they said, well, what do you think happened? And the horror was that there were 7 different opinions among the 10 people that were involved. And right away, OSHA said, well, these people weren't properly trained. And I almost had to agree with them,
Mm-hmm.
because if you don't understand what it was that happened, then there's a problem with your background understanding. So if that's the question, how did you make the decision on what you were going to do to protect yourself? Now, it's another whole issue, and this is an example of another case that we did where the crew had a tailboard about the risk of induction working on 500 kV parallel circuits. And they discussed it at length about what the issues were and what they were going to do. The guy who did the discussion, led the discussion, was the foreman, and they read their policy and they talked about what they were going to do. In the course of the morning's work, he opened up a circuit, got in the middle of it, and he did not survive his injuries. He's the guy that was telling everybody how to do it and what they were supposed to do. So, you can't ask them now, but the obvious question is, well, what was he thinking? Which is what we have to ask every time we do an investigation. And we have to look at what everybody knew, what they had talked about, and then what they did to try to figure out, well, how did he make that kind of mistake? But it really is very simple because electricity is electricity, whether it's a high voltage fault current or whether it's a 200 amp service to a house, or whether it's a distribution circuit. Electricity behaves the exact same way under all circumstances based on these principles of resistance and current flow and resistance and voltage drop across that resistance, which is what you'd have to go back to the first podcast because we don't need to be reviewing that now. But the rules are really simple. There's not very many ways to get electrocuted. You have to be exposed to a potential that's high enough, or a voltage potential, same thing. You have to be exposed to a potential high enough to break the resistance of your skin. If that voltage breaks the resistance of your skin, current can flow. And if that available current is high enough, which we say that threshold is 50 milliamps, the worker can be injured or killed. So what we say then is look for the gaps. So if I'm doing a tailboard on a distribution circuit and I'm getting ready to max some stuff out, and I've got a nearby 345 circuit running maybe on the same pole above my distribution work, and I'm going to be moving jumpers and opening and closing jumpers and stuff like that, I need to be able to stand on the ground, look at the work tasks that I'm going to do, and identify the gaps. When we say the gaps, we're talking about any opens that exist or that we're going to create during the work, because those opens represent, and we can think of it this way, an open neutral. If I've got a neutral and I cut it, when I cut that neutral, a voltage is going to appear in that gap. And that gap, if that voltage is high enough, can penetrate the resistance of your skin, and now that neutral current flows through your body. Nobody is going to cut a neutral and grab both ends of it. That's basically what we're looking for, those gaps. Remembering that everything that's grounded in our system, everything has some current flowing through it, whether it's high current or whether it's low current or barely detectable current, has simply to do with the incidental conditions of the installation and the current that's available.
Hey, folks, if you're responsible for training line workers, you know the challenges. Regulations change, crews come and go, and training must keep on top of it. That's why T&D PowerSkills is such a game changer. With 78 modules built specifically for adult learners, you can control your message, control the scale of your training program from quick refreshers to a full 8,000-hour DOL certified apprenticeship, and control your training costs regardless of whether you're a small contractor or a large utility. It's flexible, it's effective, it's built for the way we train today. Check out TND PowerSkills at tdpowerskills.com. That's tdpowerskills.com. Let's continue on here, Jim, and dig a little bit more into the distribution and URD world.
Hey, and let me say something too. I want to revisit something that we said earlier and something that I mentioned. I mentioned earlier the appendices to the OSHA standard in 1910-269. And it's Appendix C that gives the employer guidance on creating equipotential zones and grounding. Okay. And how they can go about doing that. Now, what's important about that is that if you are a trainer or a safety person, I hope you've already read that and read that diligently to understand what it says. Now, it's not necessarily a mandatory requirement. You can't be fined over non-compliance with that particular rule or that particular guidance that you find in the appendix. But the important part about understanding the appendix is that that's where the knowledge comes from for you to help you make sense of your training requirements, and what you're doing. Now, not just Appendix C, because we also have a couple of other, for instance, there is a guide written by the ESMO subcommittee, which is electrical distribution practices that are developed by the ESMO committee of the IEEE. They wrote a standard called Worker Protection While Working De-Energized Underground Distribution Systems. It's a guide. It's a practical guide for grounding in URD. The IEEE standard 1048 is a consensus standard. Consensus standards are not law, but they are best practices used in our industry, and they are referred to as conditions of care. So IEEE 1048 is called the IEEE Guide for Protective Grounding of Power Lines. This is the information that you as a employer, or you as the safety supervisor, or you as the trainer ought to be incorporating into your training, so that everybody has the same advantage of having a knowledge base to help them make decisions about what it is that we're going to do. Because like you said earlier, Mark, one no one grounding method is going to satisfy every exposure that a line worker has.
We touched on the first episode of this series, and so let's maybe go a little further here. Over the years, bracket grounding, source grounding, so on and so on, and then obviously equipotential grounding or EPZ. Let's start with the overhead world, because I think in everybody's mind that's probably the easiest visual place to start, right? They can visualize maybe a little better what we're talking about, and then we'll kind of dive into the underground world, because then obviously everything's in dirt and you can't see it, right? So, and I think people tend to maybe make some assumptions that they shouldn't, right? But how do workers practically apply EPZ in the overhead world, right? Why do we need to apply EPZ in the overhead world, right? Why are the bracket grounds not enough? Why are the source grounds not enough, right? Maybe let's try to put a bow tie on that one before we move into the underground world.
And really, there's a very simple way to explain why we create the EPZ or the equipotential zone. And it's very simple, because a traditional three-phase ground, I became a lineman. I got into the industry in the early 70s. So, we're talking about what, 51, 52 years now. And I was a climbing lineman for 20 years. I was a foreman, a bare hand lineman, and I was doing all this stuff, and I was already a lineman when OSHA was created and the rules started to come out, and everybody started to press the issue about installing grounds. And as
Mm-hmm.
I have said often in training, I had no idea why or what was actually being accomplished when we were grounding. They just said this is a rule we're supposed to follow, and we just went out and we did it. And we didn't always do it with I just say not really good, because we just we didn't know why we were doing it, but we
Sure.
also didn't have a whole lot of respect for the idea, because it wasn't being explained very well to us. We just did what we were told to do. Now, but everybody, and this is how it should have been explained to us. So what we were doing, we were evolving. We had three-phase grounding. We would go from the neutral to the phase to the phase to the phase. That's the way we always did it. And now they said, okay, now you have to equipotential ground. And when you equipotential ground, you have to make a connection from your ground point to the pole, or ground to the pole and connect to the system neutral. So now we're assuming here that the system neutral is going to be our ground electrode for grounding of our system. So we were adding this connection to the pole, and everybody says, well, it's a wood pole and it's only a piece of number 6, and the pole bond, going up to the top, or maybe the pole bond didn't even go to the top of the pole. It just depends. If you were working on a system that was built in 1940, then you had a pole bond that went up to the cross arm, ran all the way down the cross arm, and wrapped around each one of the pins that the insulators were on. And after about 1960, utilities quit doing that because they figured out that those grounds were attracting lightning, and they said, let's isolate that, and didn't send the ground any further up past the neutral unless you had an arrestor arrangement. And so, these things changed all the time, and most of the time they changed without thinking about the safety of the linemen, because the whole point of grounding out there on the structure was protection of the system and operation of the protective devices. That's what it was there for, not to protect the worker. So even when I first started to study this, I had this same question. Well, how does one connection from the neutral over to the pole make that big difference? Well, it's very easily explained by how we cut a neutral. So if I'm going to, let's say I've got a neutral that runs past a pole, and we're going to install a set of dropout switches, and they want to double dead in the neutral. So that means that now I'm going to cut the neutral at the pole, and I'm going to dead end it on each side of the pole. No lineman out there is going to go up there, catch that neutral off in a hoist, and just cut the neutral. Because if they did just cut the neutral, now we have an open neutral. And everybody knows the danger of an open neutral. If I have an open neutral and I get between those two ends, there could be voltage as high as system voltage. That's how we always explain it in our apprentice programs. And if I grab both ends of it, the current in that system is going to go across my body. So, how do I solve that problem? Everybody in the room, if I give them that scenario and ask them the question, they're all going to say the same thing. They're going to say, we're going to mac it out. We're going to take a jumper, and we're going to put it across that point where we're going to cut the conductor. And now when we cut that conductor, that jumper is maintaining the current. But it's actually doing something else too. As long as that jumper is in place, the voltage will not appear in the gap, because it's the same thing as not cutting the conductor. So the jumper has two roles when we install the jumper. One role is to continue the circuit carrying capability of the now open neutral. The other role is to bond across that gap so that there's no voltage that's going to expose. In other words, it's going to zero the potential. If I cut the neutral and I put a voltmeter across the open ends of that neutral, I'm going to measure a voltage. If I put a MAC across that gap, that voltage is going to collapse. Well, that's exactly the same thing as an EPZ. Though we don't have a complete open, we have a resistance. So the open is a resistance. Since the open is a 100% resistance, 100% of the voltage that's available is going to show in that gap.
Right.
Now, if I'm standing on a wood pole and I have an isolated B phase that's grounded to the system neutral, then there's going to be a potential difference between that wood pole that I'm standing on and that grounded B phase if a fault should occur. And it's the same thing between any of the phases, and whether I'm standing on a steel pole or a wood pole, or even if I'm in a bucket with my arm hanging over the cross arm, grabbing the conductors, maybe doing a tie wrap. If that circuit becomes energized, there's going to be a potential difference. There's going to be a gap between that grounded conductor and the cross arm, and that's going to create a voltage in that gap. And if that voltage is high enough to break the resistance of my skin, I will be exposed to the current that's available in that gap. Well, all I'm doing when I install that bonding jumper in the EPZ is equalizing the voltage. Where there was a voltage in the gap or where there was a voltage across that resistance, I'm going to equalize that voltage by bonding it across. That's the MAC. That's the bonding jumper. That's what creates the equipotential zone, equalizing the potentials. That's the reason why it is what we call intentional protection.
Hmm.
And that's the other part of distribution, and you're gonna see this one in a few minutes when we get into the underground. It's even more surprising. In our distribution systems, we have multi-grounded systems. So let me explain something else about that gap. We just talked about the open neutral, and we said that if we cut that open neutral, we could see a voltage as high as a system voltage. That's the way we teach it because that's the maximum hazard exposure system voltage. It never happens. When we cut it, if we didn't mac it out or if we have an open neutral, we don't usually have system voltage there. And why is that? Well, the reason is because that system neutral is multi-grounded. If I cut a gap in the neutral or I cut the neutral, then on my right hand side, there's a pole down there somewhere that's got the neutral bonded to the pole going down to a ground rod or a butt wrap. On my left, on the other side of the gap, there is another bond at the next pole down going down to the earth in a butt wrap or a ground rod. Now, that's most of the case most of the time. But even if it isn't at the very next pole, it may be on the one after that, the one after that. That system neutral is connected together. Let's say I have 5 feeders coming out of the substation, all 5 feeder neutrals are all connected together. So, because of that, we'll go back to the simplest one, that pole on my right and that pole on my left. On both sides of me, that neutral is grounded. So what happens is that gap is going to have a much lower voltage in that gap because even though it's not a 4 foot or a 5 foot long bonding jumper across that gap, it is a pathway from the pole on my left to the pole on my right through the earth that creates a incidental grounding bonding arrangement across that gap. And that multi-grounded neutral is what keeps that voltage much lower than system voltage. So if it didn't do that, and this is part of the engineering design, the theoretical design, if I multi-ground my system neutral, then if I have an open on the pole, it's not going to explode and destroy that pole because it's not going to be system voltage. If we didn't have a multi-grounded system, then every neutral in our system would have phase to phase voltage on it. And then every time we had an open neutral or a bad connection on a pole, we'd have arcs and flash and we would burn a hole through the middle of the pole and the pole would fall over. But we multi-ground the pole in order to keep that open voltage low.
Hmm.
That's the same thing we do when we bond a pole for our protection. Is that jumper that's going from the pole to the phase is bonding out the difference or bonding out the gap that our body would be replacing, and making sure that that voltage is low.
I might be stating the obvious here, but I think it's important to point out that, those pole bonds and the pole wire grounds that go to the ground rods, whether it's at every pole or whether it's every other pole or every fifth pole, whatever, all that stuff is installed and engineered for protection of the system, right? And to take into account lightning strikes and faults and so on, so that there's direct pass to ground to get that energy out of the system, to your point, so we don't burn poles down and damage equipment and so on. That stuff, those specifically pole grounds and pole wire grounds and so on, are not installed for the intended use of your personal protective grounding system. And I think that's a very important distinction to make, because I have had arguments with people in training classes that, well, every pole has a pole ground. And so I'm grounded to the neutral, right? And so if something happens, I got all those points going to ground. That's not what they're there for, right? They might have been installed 30 years ago, right? So how good's their integrity? How good's the pathway? I think it's, again, maybe stating the obvious, but I think it's an important distinction to make, that those pole grounds and pole bonds and so on are not there for your personal protective grounding system.
And let me mention here, I think I can do this without getting in trouble because they've published a paper on it that's still available. AEP, very large holding company utility that has a number of utilities across the east, from Ohio down, I think, into Virginia, and across from the central states over to the east, a number of different utilities. So AEP decided to test exactly what you were talking about. In a little bit, I'll get back to whether or not you have to use the big clamp on the pole, or the what does everybody call that? They sometimes were called a grounding bale, sometimes they were called a
Cluster bar.
cluster bar, yes, stuff like that. So there's been a lot of questions about that, and that's the question AEP had. And so AEP decided to do some research, and they said, what about that bond connection? So this is where and here's some essential knowledge that everybody needs to have. And it's similar to what you were talking about a moment ago, and what we have called uh, um, incidental and intentional. So a pole that was installed 40 years ago has a pole bond installed to a ground rod connected to a system neutral. So that's a 40-year-old connection, and it may or may not be good. And so AEP decided to test, well, does that pole bond connection provide equipotential for the worker on the pole? And they found out that a lot of existing pole bonds would suffice as protection for the worker, but not necessarily could it be depended on to provide that protection, because many times I'm assuming, I think I remember what they did. They took poles from the field and rolled them into their lab and ginned them up to see what was going to happen. And so they got a very good matrix of what actually did happen with those existing pole bonds. Well, see, this is part of what has probably kept a lot of people thinking that bracket grounding worked, because in the 20 years that I have been teaching equipotential grounding, I would hear comments all the time. Well, I know some guys that did this and they were bracket grounded, and they felt a little shocked, but nobody got killed. They didn't get hurt. And that's because of this incidental level of protection. And it goes back to that idea of the multi-grounded system. And it's just like you said, Mark, it was there to provide system protection, effective system protection and relay to trip circuits so that it wouldn't damage equipment, and it would limit the amount of fault current that would be in the field and damaging equipment. It wasn't there to protect workers. But what they also found out was that if they went back and they added a connection to the pole, then they had an intentional bonding connection that did perform, and it did work to protect the worker, to keep that voltage to the worker low. So actually what they were doing was the exact same. I could take a number 2 insulated cable with a ground clamp on each end, and I could put one on the pole bond and one on the one on the neutral, or I could do it with a piece of number 6, and either one of them, or a piece of number 4, either one of them is going to provide that bond across that open. Now, the pole bond plays a role too, because the pole bond is strapped to the outside of the pole, and it's stapled to the pole, and that staple is the bond connection between the wire on the pole and the wood of the pole. Wood, we used to have hot sticks made out of wood, but they were special kind of dried out wood, and specially protected. And we might say, well, wood is a good insulator. I could switch a transformer with a tree limb. No, no, you can't, because that tree limb is somewhat conductive because of the moisture that's in there. Well, poles are considered conductors themselves, even though they're not very good conductors. We have a lot of numbers that tell us how good different kinds of wood are at conducting. And then we also have the outside of the pole, which is very dry, and then a little farther inside the pole, there's moisture. So if I drive a 9/16 of an inch long staple over a pole bond into the wood, I'm making an electrical connection between the pole bond and the pole. Now, the number of staples that I install are going to make a determination as to how good of an electrical connection I have. Well, down at the bottom of the pole, we usually put the staples, depending on the utility, 6 inches apart or 12 inches apart, up to 8 feet off of the ground. And that's pretty common standard. Now, I used to think that we did that to keep people from stealing the pole bonds, but that is not quite true. The electrical theory was that the more pole bond staples I had down where the general public walks around, the better bonded my pole was to the earth. So a person walking past the pole or leaning up against the pole waiting for the bus, if the pole should become energized, that pole was well bonded to the earth that individual was standing on, and the resistance for the worker and the voltage across the worker would not be high enough to result in a lethal injury. So the reason why those staples were every 12 inches was to increase the bonding of the pole for the protection of people that were on the ground. Once we get up over 8 feet or 10 feet or 12 feet,
Mhm.
depending on your standard, now we put them about every 6 feet apart until we get up to the neutral. Then we drive one staple in on the pole bond just above the neutral, and then we fold the pole bond down and put it in an A to Z clamp, and we bond the neutral. So what we wanted to do then was that if the pole bond could be or may not be a good connection because it's incidental. So now what we have is a number of utilities that have done the testing, including AEP, and they figured out that what we could do is install a number of staples 6 inches apart for the first 6 feet, and there's a number of different. I'm not. We're not saying here that this is the way to do it. Do your research if this is what you're going to rely on. But we have utilities that simply go up and add 4 feet of number four, stapling every 6 inches, making a connection to the neutral, and using that as a bond to create a bond for that grounding system on that pole. Now, I don't care how you do it or what you choose to do it. You do your research. You got to be able to defend the connection that you're going to make. But what's important is that you do have a good electrical connection, because that electrical connection, that is that bonding jumper across that open neutral. Remember, we said our
Mhm.
example is an open neutral. It'll kill us if we grab it unless we put a bonding jumper in there to equalize the voltage. That's what we're doing. Now, there's something else to remember here about how EPZ works. This is the exact same way that we test our grounds. We use a 200 amp generating device. It's really just like a big welding transformer. It's called a grounds tester. It's got an electrode on each end of the box. We take our 40-foot long ground or a 30-foot long ground, and we put one end on one electrode and the other end on the other electrode. Then we turn on the grounds tester and we ramp the current up to 200 amps. And then we look at the voltmeter, and the voltmeter is testing the voltage across the length of that ground cable that is carrying 200 amps. Now, there's a graph in the tester that says that if that ground cable is performing in the way that it's supposed to, with the appropriate amount of resistance, it will have this amount of voltage. And so it'll say, like, if you look at the graph for a 30-foot long 4-aught, it might say something like 5 volts or 8 volts. I don't remember what it's supposed to be. It depends on the size of the cable. So I ramp up the current to 200 amps. I look at the voltmeter. If the graph says it's supposed to be 8 volts and the meter says it's 8 volts, the ground is good. What that meter is telling you is that in a 200 amp fault current coming across that ground, that a total of 8 volts is going to be generated across the length of that conductor. That voltage across the length of that conductor, that's the voltage that you're going to be exposed to on the pole. Now, you take into account that that pathway for the purposely installed jumper, that's my intentional bonding jumper, has collapsed that voltage down to a meager 4 or 5 volts. The voltage across the jumper is the voltage that the worker is going to be exposed to. So the quality of the connection from the neutral to the pole, because we say the neutral because that's what we've grounded our three-phase to, the quality of that connection is going to determine the voltage that that worker is going to be exposed to. So the better our connection, the better our cables are, the lower the resistance of that connection, the better the protection for the worker. And one of the very interesting researches that was done was Bonneville Power. I'm sorry, Puget Sound. This was done in 1988, and I think you can still find the results if you search for it online. I don't know if you can get Puget Sound doesn't exist anymore as Puget Sound. It has grown and divided and been taken over by a whole bunch of different people, just like a lot of other utilities have over the years. So it's harder and harder to find the information. I found it 20 years ago when I was doing some of this initial research. But they have a graph in there where they use a number of different connections, and they created a table of exposures based on the different types of connections that were made, and showed those exposures across those workers. And by the way, they were researching the effectiveness of bracket grounding too, and they confirmed that bracket grounding does not ensure protection. That no matter what bracket grounding that they did, they always exceeded the threshold of risk for the worker, which is at 50 volts and 50 milliamps. So that's what we're doing, and that's the reason why the pole bonds provide this incidental level of protection. So you need to make a decision about how you're going to bond that pole in, because it really boils down to it's just this one connection. That one connection from the neutral to the pole, it has to be good, it has to be intentional, and it has to be sufficient to collapse that voltage that could appear between the worker on the structure and the conductor if a fault should occur on that grounded conductor.
Now that we kind of know the theory behind the overhead and the equipotential grounding with the pole bond, or the intentional pole bond, I should say, let's drop down into the underground world, right? Because I'm pretty sure we have both. I know I have, and I'm pretty sure you have. Tend to find folks doing some things in the underground world that they would never think of doing in the overhead world, right? And I think a lot of it is because they don't understand the why. When we drop down into the URD world now, what changes when it comes to EPZ? And kind of how do we ensure that we maintain that EPZ effectively, right? And I think there's some things, again, that you're going to talk about that guys would agree, well, I'd never do that up on the pole. Well, then why are you going to do it on the ground, right? It's the same thing.
Actually, there's a funny thing about this. I write the 101 Train to Trainer for Incident Prevention Magazine. And about 12 or 15 years ago, and I can't remember, how long it was, I wrote an article called Why Equipotential Grounding Works. And I did a detailed description of what we've been talking about here, and we're going to be talking about over the next couple of podcasts. A detailed description of explanation of why it works, why it's so simple, and why we're supposed to be doing it. And I used examples from the overhead. And so the very first thing that happened, and I can't remember, but I think there was like 4,000 downloads, of that article. And a whole
Mm-hmm.
bunch of people also emailed to incident prevention saying, well, can you write an article on doing EPZ in the underground? And I hadn't even thought of that. And so I started thinking about it. And the first thing I do, and it's the same thing that we do when we're doing an investigation about how somebody got shocked. We draw out an electrical circuit, the components of everything that was involved in that electrical contact. So I did the same thing with a pad mount transformer. And you remember that everything is connected together and everything has a resistance associated with it. And we want to bond out all of those different resistances. Well, up on a pole, that's pretty easy to do because the only resistance we have is between the pole and the phases and the pole and the neutral. The rest of it's sky.
Mm-hmm.
We don't have to worry about grounding the sky or bonding the sky. We only have to worry about bonding in our exposure in that very well-defined area. Well, in the underground, it wasn't the same thing because when I drew it out and I applied resistances and all those combinations, what I found was, ooh, we got the resistance of the ground, and I'm thinking about all the years that I worked on underground on my knees in wet dirt, or damp dirt, or you know, leaning up against the transformer apron, on the pad mount transformer and handling the system neutral, and stuff like that. And when I drew that out, I said, can't do it. you, you really can't bond yourself in.
Mm-hmm.
The reality was it was very, very, very hard to do. And so I wrote an article about grounding in the NURD about the difficulty of trying to put everything together. Because besides the fact that I might have a ring bond inside of a pad mount transformer, and that ring bond might be bonded to the concentric neutral on the cable that I've got in my hand, but that cable runs 300 yards down to the next transformer. And if I'm replacing that cable, but let's say I got to replace a URD elbow. Well, if I've got the concentric grounded and I pull the elbow off and I grab that conductor to put a new lug on it, that lug is grounded 300 yards away at the next transformer down the line. It's not grounded right there where I am at. So there is a difference in potential between that ground 300 yards away and the concentric that is 4 inches below my hand where I'm making that connection.
Mm-hmm.
So if a fault hits that system, there's no guarantee I'm not bonded together because of the
Yep.
distance they are away. So, I mean, you can't, they would put out an equipotential mat and they would connect it to the concentric on the inside of the transformer and stand on the mat and say, look, I'm bonded in. No, you're not, because that conductor, because you're grounded at the other end, that conductor that's sitting on that stanchion, that grounding stanchion, that next transformer, has put that phase conductor parallel to that concentric.
Mm-hmm.
And what do we know about concentrics? That concentric is a system neutral. So if it's a system neutral and it's part of a three-phase system, it's always going to have current on it. So if I just put the phase conductor parallel to the concentric, I simply created an open neutral when I pulled that elbow off and exposed that phase conductor. Now that's worst case event. You can imagine what would happen.
Right.
Most of the time, it doesn't, and we'll talk about that in just a minute. But it doesn't create a hazard, and I'll explain to you why. And again, it's incidental, not intentional. But a transformer is a little bit more different than working inside of a ditch. Because if I've got an open conductor in a ditch, and I've done it hundreds of times as a lineman, see, I would go to a trouble call with a bad neutral connection or a pole hit or something like that. And if I had to open the neutral, I would mac it out. I would never cut that neutral or open a neutral without macking it out. But I finish that job and I go to a URD open and I get down in a ditch with a cable and I repair the cable and then I grab both ends of the concentric in my hands and I put them together on a squeezed copper linkage. What's the difference? There is no difference. The concentric neutral wrapped around the outside of that URD cable is the system neutral. And if I'm in that ditch in the dark and I put those two concentrics together, I'll see little sparks. Anybody that's ever done it in a little, yeah, sometimes you can see it in the daytime, but you can always see it at nighttime if you're out there
Yep.
putting it together. That indicates there's current on that, and that's current being divided among the three-phase circuit. Because remember, our first rule is current flows in every available path. So if I've got a feeder going into a residential area and I have A Street and B Street and C Street, and I've got A phase on A Street and B phase on B Street and C phase on C Street, and I'm working an open on B phase, when I've got that open, that's part of the total current carrying capacity of the neutral for that three-phase system. So there's always going to be current flowing there. Ha! Now we come to, okay, so we've got 1,800 linemen made splices on URD cable this week, and none of them got electrocuted, and they all did a bare hand assembly of the concentric when they finished with it. How come none of them got hurt? Well, it's because of the incidental design of the system. Remember, we got A phase on A Street, B phase on B Street, C phase on C Street, and I'm working on B phase. Well, I can't mac it out. I can't mac out the phase conductor because I essentially have to keep it clean. I can't assemble it if I've got it macked out, but I'm handling it. I put it together. I do the same thing with the system neutral. Well, incidentally, at the transformer to my right and the transformer to my left, there's a ground rod that's grounding that concentric into the earth. I didn't put a Mac across that concentric before I assembled it, but I had an electrical connection across my open on B Street that is maintained by A phase and C phase, running parallel right past me, essentially operating as a bonding jumper, incidentally bonding and grounding that concentric in my hands so that that voltage is low enough that I don't get hurt. And now there are people that are going, oh, well, I can rely on that. No, you can't because you don't know for sure how do I know the cable just blew up on B Street? How do I know that the one on A Street's not getting ready to blow up also? You can't say that it ain't gonna happen. I remember replacing a pole hit by a drunk on a corner on Oakland Park Boulevard in Fort Lauderdale when I was a lineman. We were out there for 4.5 hours replacing everything, got it all done. There was a Dunkin' Donut across the street. They said, when you get the lights on, come back over. We'll give you some coffee. We finished it, got it all done, and then we walked over to the Dunkin' Donut, and another drunk came by and hit the same pole that we had just repaired. Now, if we had been there 2 hours later, he would have plowed right through our work zone and hit our trucks and hit our pole. What are the likelihood? What's the likelihood of that happening?
Yep.
That's very, very, very low, but not impossible. And it's the exact same thing as working with that concentric. It's very, very low possibility that we're going to have a fault on that cable, while we're working on it. But it certainly isn't impossible because the one we're working on just blew up.
Yep.
So how do we know that the others won't also? So we have an exposure there. We have an incidental condition that has served to provide protection for us and made people think that there isn't any risk.
Yep.
Which is the reason why people go in those ditches every day and they do that. And so I started thinking, well, how do you protect yourself from that? And then I remembered what I've been teaching for years. There's a number of ways that we can do work. One is we can work it hot, which that's not practical at all for underground. We can ground it and bond ourselves in, which is not easy to do with underground, or we can isolate it. If we isolate it, if we create an open on each end of the cable, which that means that when we park the elbow, we park it on a standoff bushing, not a grounding bushing, but we ground it first time. And then when we know we've got grounded that cable, now we pull it off, we take the grounding bushing off, and we put a parking stand there, and we park that cable. Now we have isolated the phase conductor. Then we go to the concentric for that cable, and we cut that concentric free of the transformer. When we do that, we have now isolated the phase conductor and we have isolated the concentric. Now, there is one other thing that we can do. If we take that grounding bushing that we park our elbow on, and we take the ground lead from the grounding bushing and we put it on the concentric right there at the cable, and we cut that concentric free of the transformer, we've now created an electrical path from the phase conductor to the concentric that is isolated from the system, that provides one other means of protection. A capacitor is two conductors separated by an insulating medium. Everybody knows that a phase conductor is a URD conductor is a capacitor. We know that they will hold a charge. And sometimes people have gotten shocked on those. Well, the way that we solve that problem is we connect the two together, just like we short circuit a capacitor. Well, if I do that, then I've short circuited that capacitance of that cable. It's no longer a capacitor. So I've also eliminated the possibility of capacitance on that cable. But isolation is a solution. And when I wrote that, a whole bunch of people wrote into incident prevention saying, he's crazy. You have to ground it. The law says you have to. Well, that's how I found out about the IEEE guide for protective grounding of power lines. Because when the ESMO committee was working on this guide, and they wrote the paper Worker Protection While Working De-Energized Underground Distribution Systems, one of the possible recommendations they made was that isolation of the cable may be more effective than trying to equipotential ground. And it's funny because there was a guy on that committee that was writing this paper. It had not been published yet. I wrote about this possibility of isolating in incident prevention. And he called me up, wanted to know if I had a bootleg copy, of this thing that had not been published. Nope. I did the exact same thing they were doing. I was trying to solve a problem and realized that, hey, isolation is a solution.
Yeah.
So it's the same thing. Overhead, underground. If we can't effectively ground and bond a worker in, if there are no other sources of energizing, isolation is another legal way of doing that work.
We're kind of at the end of our time, Jim, for this episode, but again, kind of just like I did in episode 1, that one takeaway, right? So whether you're the line worker, the safety professional, the supervisor, when it comes to overhead and underground EPZ, if nothing else is taken away from the last hour of conversation here, what is the key that you want to make sure everybody understands about overhead and underground EPZ?
When we do work in the distribution, it's not always easy and it's not always quick. And sometimes we spend a lot of time, a lot of hours working. And sometimes we might want to take a shortcut. Now that we understand the nature of these risks, such as constantly circulating current and the difference between incidental and intentional bonding of a system to protect a worker, and we realize that there is a possibility that those incidental protections may fail to protect our workers. So that's the reason why we use the intentional. That's an important takeaway. But for the supervisor to recognize this, you are both ethically and legally responsible for the welfare of your crew. You know, and we have been training people to do it the right way. You know what the right way is. Do it the right way. If you have a policy and a procedure, follow the policy and procedure. Nobody can hold you accountable, either ethically or legally, if you did what you were supposed to do.
Yeah.
You can be held responsible unless you followed the rules, even though something may still go wrong. If you did everything you were supposed to do, you're not going to be exposed, and most likely nobody's going to get hurt, and you'll never even know
Right.
about it. So, following the rules, intentional as opposed to incidental.
Yeah. All right. Again, if you have questions, they can be sent to Mark at ispconline.com. We'll go ahead and compile those, and one way or the other get you the answer. Depending on the amount of questions we get, we may do a sixth episode to discuss those Q&As. Training and safety professionals face more pressure than ever to keep their line worker programs compliant, current, and cost-effective. T&D PowerSkills offers a 78-unit curriculum that gives you total control to customize the training content to match your specific needs, control over your delivery, whether you're doing short refreshers or managing a full DOL-certified 8,000-hour apprenticeship. And best of all, you can control how the program scales to fit your operation, no matter the size. It's trusted by utilities and contractors nationwide. Visit tdpowerskills.com and see how you can take control of your training. Again, that's tdpowerskills.com. And in closing, the views and opinions shared in the podcast are the personal viewpoints of the participants and may not necessarily reflect the stance of the Institute for Safety and Powerline Construction and its staff. It's highly advised to consult your company management before implementing any actions or policy changes. Please support the sponsors bringing this content to you. And for more episodes of ISPC Tailboard Talks, subscribe to your favorite podcatcher and be sure to leave a review. We'd love to hear from you. Jim, appreciate your time today as always and your viewpoints and your years of expertise and research into this. Again, for everybody listening, this is going to be a series. This is episode number 2 of that series. We have 3 more to go. Make sure you check your favorite podcatcher for these episodes. And until next time, so long, and we will catch you on the next episode of ISPC Tailboard Talks.